is now being recorded.
Hello, everybody. Welcome to the last Cyberseminar of the fall series. My name is John Pollack. I'm the Youth Support Specialist here at Quasi. Before we get started, I'd like to just announce that we will be having a spring series starting in February with a focus on snow hydrology, so I hope you all will be able to join us then. But now I'd like to introduce Todd Rasmussen, who is a professor of hydrology and water resources at the University of Georgia and also a member of the Quasi Board of Directors, who will introduce today's speaker. Thanks, Todd.
Well, thank you, John. Hi, I'm Todd Rasmussen at the University of Georgia, and I'll be hosting today's Quasi Cyber Seminar. And our guest speaker today is Daniel Rothman, who is a professor of geophysics in the Department of Earth, Atmosphere, and Planetary Science at MIT. His talk this afternoon is on the branching of stream networks. This falls in line with our current series looking at landscape and channel characteristics. Professor Rothman received his AB from Brown University in 1979 and his PhD from Stanford University in 1986. He is a theoretical geophysicist who has contributed to the understanding of the dynamical organization of the natural environment. Professor Rothman's current work combines theory, field observations, and experiments to study problems including the carbon cycle and climate, the coevolution of life in the environment, and the dynamics of fluids, rocks, and sand. And thank you, Daniel, for speaking to us today.
Okay, thanks, Todd. So I'm going to be talking about just a subject which you hopefully can see right in front of you, the branching of stream networks. And this is joint work with the named listed above, Olivier Devauchel, who is now a researcher at the Institut Physique du Globe in Paris, Alex Petrov, who's a postdoc at Rockefeller University, and Hans-Jörg Siebold, who's a postdoc across the hall from me right now. Right. So let's see if the page turns. Okay. So here is a beautiful picture that represents or shows the kinds of structures that interest us. And one of the things that you'll notice, I don't have such easy access to a pointer, so I'll just describe this in words. You can see basins within basins within basins, and I'm sure many of you are already familiar with that concept. And you also see many successive branching events, and sometimes we think of them as ramification events or ramified structures, and that's what we refer to as dendritic. So the question that motivates the work that I will describe is basically written in red below. It's how does such dendritic networks grow? Now, that's a very broad question, and to be entirely truthful at the moment, I'll tell you that we're going to examine a piece of that. There's much that remains to be done, but I think we have made some progress on an important piece of it, and that's where our talk will be headed. So we'll in the end, present, I think, some significant insight on how these things branch, right? And that's basically the subject of the talk. So when I say these things, I do mean such dendritic networks, but I'm going to specialize our view of them, and I'm going to discuss a subset of the types of drainage networks one can see. And in fact, it will be a very special subset. It's a subset that will allow us to make some progress. And from that, I think in successive work, we'll probably, I'm sure, we will have some insight as to the more general problem. So let me speak of what I just referred to as the more general problem, and indeed I misspoke a little bit. It's not a more general problem, it's a more common problem. And the commonness of it is in reference to people's conception of how erosion works. If you examine most models of landscape evolution today, by and large, they all consider in one fashion or another, or many of them consider in one fashion or another, erosion to be taking place by effectively a sheet of water that's flowing over the surface. It doesn't, these models don't necessarily say that explicitly, but by considering water as deriving from a certain kind of drainage area, effectively that's what's meant. And in these models, the salient feature of such models is that water focuses at channels or at channel heads, at rivers. And that focusing is a complicated yet direct consequence of the topographic shape. So any little bits of roughness on the overlying surface will lead to focusing of the flow into a channel. And because of that, the problem is complicated because one has to take into account all of the features of a surface to understand where the flow might go. So we, on the other hand, are going to study a simpler problem, right? Or I should say, when I say simpler, it's a problem that's easier to understand, right? And the problem we're going to study in this talk is the problem of erosion that's caused by the seepage of an aquifer, of a hydrologic flow, of a subsurface flow out to the surface. So the difference between the picture before and the one now is simply that the water is largely submerged, and then it eventually comes out there on the right-hand side into what's commonly called a seepage phase. And then it starts focusing based on what it does above the ground. But the advantage to this particular perspective is that in a steady state, the shape of the topography above the water table doesn't really influence the shape of the water table itself. And as you'll see, using, as I'm sure most of you know, using commonly understood concepts in hydrology, we can basically understand what the shape of the water table is. We can understand what the flows will be. Precise equations can be written down, and we'll work out what they mean. So in what follows, we're going to focus on this subsurface seepage flow problem, which, as noted here in the first bullet, is inspired in part by some work of Tom Dunne from some time ago. I'll make reference to Dunne's work again in the future. Right. So first of all, this stuff is fairly common. You just have to know what to look for. This is a picture, obviously, of a beach, right? And what you see are these rill patterns on the right, sometimes called beach rills. And the way they form is that when the tide goes out, as you see here, there's some seepage flow coming, that the water table doesn't recede as fast as the tide goes out. And some of it ends up seeping through the sand and it erodes these channels. So that's what it looks like on a small scale. And now I'm going to show a succession of pictures which are not necessarily the same phenomena, and that's why there's a red question mark at the end. But my point in showing you these things is that some people at one point or another in time have associated such features with the seepage phenomenon. And this is a picture of one of the levees outside of New Orleans, and the large-scale rills, the channelized features you see at the bottom, are thought to be associated with some seepage flow. And moving further around, these are some submarine canyons, in which you'll notice that the head of the canyons do not appear to connect to anything. And so some people have suggested that such submarine canyons are the result of submarine hydrologic flows, that is, hydrologic flows beneath the sea bottom, which are flowing out and creating such channels. There are other hypotheses for how they form, but I'm just pointing out that there's some interest in this problem because of that. And this picture here is, now we're largely, many of us are familiar with the idea of channelized features on Mars, and for some decades, ever since the first Mariner photographs were taken, there's been a lot of speculation about whether those features have anything to do with seepage of groundwater on Mars. Again, note the red question mark. I'm not saying that they are the result of that. I'm just saying that many people have asked whether the problem applies. So we're going to go to a place in the field where there is no red question mark, right? Where we know what's going on, and where seepage is unequivocally a major player in shaping the landscape. And this is a field site which is on the Florida Panhandle. It's about midway between Tallahassee and Panama City, right? And these features are known as steep heads. They're cut through essentially ancient beach sands. I'll show you photographs in a moment. But just this old-fashioned geologic map, you'll see modern ones in a moment, but this old-fashioned geologic map still contains some detail that don't necessarily show up on some others. These are basically valleys which are incised by seepage. On the left of the picture is the Apalachicola River. The valley depth is about 20 meters. The width of the valleys is about 100 meters. And most importantly, the infiltration rate is really fast. It's about 30 centimeters an hour. And because of that, one sees little to no evidence of any overland flow. Because when the water hits the ground, it goes into the ground. Right? And it's thought that the valley heads are advancing at about 1 millimeter a year. When I say it's thought, Stan Schum, who worked in this area some years ago, made that statement. We've made it in some other ways, and there's still more work to do, but that's probably more or less how fast they're moving. Right. So this is what you can get at your desktop. If you, I can imagine now everybody's going to do this. You go to Google Earth or Google Maps, type in Bristol, Florida. That's B-R-I-S-T-O-L. And you go north a couple of miles along the river, you'll see these lovely features. And the valleys are given, are green. If you look carefully, or you take the Google Map version and expand it, you'll see there's a sort of darkish outline within these valleys, and that's where the streams are flowing. And the reason there's such contrast is because this used to be a tree farm and is now being restored to its original grasslands by the Nature Conservancy, and the Nature Conservancy office happens to be that little white speck in the upper left-hand corner. So this is now this sort of topographic map, one looks at instead of going to the old paper versions. This is a LiDAR map, and you get a much better view of the structure of this network. And you can see there's, a bunch of interesting features. Again, I don't have easy access to a pointer with this tool, but we'll make reference to a fair bit of them. And suffice to say that there's a fair bit of branch structure, and that our focus will be on the branching itself. This is what it looks like when you're on the ground. Right? These are these valleys come to a head. They're called steep heads. I'll show those in a minute, but they're cut into a flat plane. The flat plane is on the right. The valley walls, or a valley wall is shown on the left, and you can see it's fairly steep. this is what it looks like when you're inside the valley. On the left, you can get a perspective looking at the people. You can see that the valleys tend to be on the order of 100 meters wide. And then the water table is, if the valleys are about 20 meters deep and the water table intersects the valley at a spring, on the left-hand side, you can see where the head of the spring is. You can see that sharp incision into the valley. And on the right-hand side, you can see an actual spring. Right, and it's adjacent to, just to the right of the feet of my colleague Alex Lubkowski over there. And it's whitish because the underlying sand is a light color compared to the organic debris above it. And so, in fact, you can go there. Of course, you can go there. You can see we've been there. When you go there, and if you look down at the spring, you can see erosion happening in front of your eyes. Basically, a sand grain is always coming out of the subsurface, and the integration of those sand grains over time eventually creates slumps around it, and it creates these almost semicircular valleys that you see on the left. Okay. So we are not the first people to be interested in such phenomena, and I think it's fair to say that the most influential, or at least from our point of view, the most influential of the early papers on the subject were written by Tom Dunne, who studied seepage erosion, I believe, as part of his PhD thesis in the late 60s, and this is a paper written shortly thereafter, but it's similar to the material of his PhD thesis. And basically, Dunne nicely identified the major the major mechanisms responsible for the growth of these types of channelized networks. On the top, you can imagine that horizontal line at the top being the Apalachicola River. Eventually, there's a perturbation. That perturbation attracts subsurface flow to it. The perturbation grows, and you can see that it's growing because there's more fluid going to its head, less to its sides, right? And then eventually there's another perturbation from its sides, and that's how you get a network, and a sort of ramified network, which is shown there on the right. So what we've taken as a kind of challenge or problem statement is essentially to, shall I say, mathematize these cartoons. Right? And I say cartoons with utmost respect. I think the main features are there in front of you. What we're going to do is write down a mathematical model from which we can learn more than you can see in the cartoon, so that we can add to this understanding that's already present. So, and the first step is to apply standard concepts of hydrology, and that allow us to approximate what is clearly a fully three-dimensional problem as basically a two-dimensional problem. And we'll basically solve for the height of the water table and therefore the hydrologic flux in the network. And as I'm sure most of you know, this is basically the standard construction of the Dupuy-Forchheimer equation. One takes the water table to be approximately flat. You write down an equation for the flux, which ends up being a product of the thickness of the water table, h, and the gradient of the thickness, grad h, where k is the hydraulic conductivity. The next statement is one of rainfall, p, and incompressibility. And the combination of those two yields the famous Dupuy-Forchheimer equation, which in other parts of physics is, of course, known as the Poisson equation. It's a Poisson equation in the height squared, where height is the thickness of the water table. Right? And the driving force is, of course, precipitation, and the hydraulic conductivity is, again, K. So this is essentially the system from our point of view, and we're going to work out its ramifications. So first of all, before we do work out its ramifications, we're going to basically tried to convince you that it works. Now, this theory one reads about in textbooks is correct. So now, of course, we all knew it was correct, but we're going to establish that it characterizes what goes on in this Florida network. So this is just a computation of the water table height in which the valleys here act as absorbing boundary conditions. Right? Of course, you can then compute the flux lines, and you can compute the flux to the walls. It's really a flux to a stream, but in this particular formulation of the problem, it's to the walls of the valley. But we can do it either way. I just happen to like this picture. Now, what we also do is measure the actual flux. And the measurements are at these locations where you see these light blue or gray dots. So we measure the flux at those locations, and then we compare it to the predicted flux from this numerical solution of the Poisson equation with the boundary condition given by the network. And the way the measurements are done are as crude as can be. We measure the width of a stream, and this is a stream just below a spring. We take a length which is on the order of a few meters. We put a twig in the stream and time how long it takes that twig to go from one end to the other. And with a stopwatch, you get a rate, and with the depth of the stream, you get a depth and a width, and in the end, you have a flux. It's sort of trivial, and that's what it previously was what it looks like at a spring, and here's what it looks like near the outlet. So it's of course much wider, but still not so deep and not so wide that you can't manage it. And then we put them all in a plot, and it all just works. Right? And the way there's no adjustable parameter on this. Is everything okay?
Yeah, everything's okay. That might have been you getting another call, maybe?
Oh, yeah. Yeah, well, I won't take it. Okay. So, basically, there's no free parameter on this plot. It's simply scaled by the documented rainfall rate. And so the documented rainfall rate gives a predicted flux, and then we compare that. It gives a predicted flux for the area over which this network is taking in water, and then everything is scaled to it, and that's compared to the measurement. And so within the considerable scatter of the plot, you can see it works well. Okay. The next demonstration for you that indeed this is a network which is driven by seepage is to do a ground penetrating radar survey, and a ground penetrating radar survey is done in that yellow box you see, and we're basically going to see if the water table is bending towards the channels as we expect, and then to see how it conforms to the theoretical prediction. So this several years ago was the first time we did it, and it was a disaster. The antenna is too small. And that's Kyle Straub, an MIT graduate there on the right, now at Tulane. And this is, again with Kyle, this is the version that worked. It's a bigger antenna. And just to go back there, I think that nicely shows you the kind of sand we're dealing with. That's the sort of sand that's throughout this site. Right. And that's a picture of the when all the data is processed and we locate the water table on each GPR section and plot it all up. You can see a picture of the survey tracks there, and and the color gives the height, and you can see there's about 4 meters of relief on this water table. It is indeed bending towards the valleys, and roughly speaking, it fits the Dupuy-Forchheimer or Poisson theory. Although in that particular plot, there's 2 degrees of freedom in fitting the data. And it's also consistent with hydraulic conductivity that's sensible. So the upshot of all this is that the classical theory is good, right? It's you write down the Dupuy, you make the Dupuy assumption, you write down its consequences, you get that Poisson or Dupuy-Forchheimer equation, and you characterize what the water table would be, you estimate fluxes, you estimate water table shape, and it basically all works. So, and the question is, what can we do? So, the remainder of the talk focuses on the question at the top. At what angle do streams branch? This is a slope map, which looks pretty much like the topography too, but it's a slope map. And you can see a number of stream branching events. Up there at the top, you see a tiny bifurcation. Below it, you see a bigger one, and below it, you see an incipient bifurcation. So, question is there an angle that streams branch at? Is it random? Is it something that physics can help us understand? And that's where we're going. So, to give you again an idea of what this looks like, that map on the bottom is just the same picture you saw previously. And up there in the photograph labeled B is a stream head. The photograph labeled C is an actual bifurcation, and the water in that picture is exiting the photograph in the upper right. Right, and the picture was taken from atop a tree by Alex Petrov. So this is another rendition of the same features. So that's a set of bifurcated tips. We're going to simplify this problem by focusing on just one of them. And we'll simplify it further by putting it right side up and focusing on the angle of the bifurcation, alpha. And we'll simplify it further by converting that into a model of, you might consider that a fishtail, in which that fishtail has one free parameter, which is its opening angle alpha. And then we make an important physical observation that, as we showed in the previous set of slides, the Poisson equation does a nice job of characterizing the hydrologic flow here. There's no disputing that at all. What we're going to do now is note that when we're close to the channel tips, the right-hand side of the Poisson equation can be taken to be small, and we're going to set it to 0. The reason it can be taken to be small is that near the tips, most of the water that's going into the tips is coming from far away. It's not coming from the region very close to the tips. So there's a separation of scales between if we were to draw a little circle around this, or we take the tip area to be very small, we can consider the fluid going into that area to be coming mostly from afar. And so we can take that boundary condition to be infinity and neglect precipitation within that region, and then that turns the problem into a Laplace problem in which the right-hand side of the system is set to 0. So it becomes a Laplace equation in h squared, the thickness of the water table. Okay. And then we simply solve Laplace's equation. This is what you get with solving Laplace's equation in the case that I just showed. And we're going to focus on the streamline that goes into the tip. And so this is difficult to render with the software we have for this talk. But I think you get the main idea. There's a flow field there, and in the flow field you can identify a streamline that theoretically will go into the tip, and that's given by the red paths. Next, we're going to make an important assumption. We're going to assume that that if that fishtail represents an incipient bifurcation, which direction do the bifurcated tips grow in? We're going to assume that they grow in the direction of the streamline that's coming into them. So we're going to find out what that means in the next slide. So in the next slide, we have 3 examples of such bifurcations. So focus for a moment on the top row. Recall for you again, we'll focus on that angle alpha. When that angle alpha is wide, as you see in the plot labeled A, you can see that the streamlines coming into the tip seem to be closing a little bit inward if you were to follow them outward. So that incipient bifurcation follows those streamlines. It's going to tend to close. Right? And the plot labeled B just below it is a close-up of that streamline. And you can see that it's a close-up corresponding to the grayed out piece in the plot labeled A. So it would tend to bend inward. You can think of that as a consequence of competition with the parent stream. Now, if you scoot to the right and consider the case E, the diagram in the upper right, here the bifurcation angle is very small, of the incipient bifurcation angle. And now the 2 child streams, the 2 bifurcated streams, compete with one another, and they want to grow apart. And that they grow apart is again emphasized in the plot labeled F below. So you can reason that there will be an intermediate case given by C in which the streamline comes straight into the tip, right? And that's confirmed by the picture D below. The streamline is coming straight into the tip. And so that turns out, and as I will explain in the next slide, that turns out to be a special angle. And that angle is exactly 2 pi over 5, or 72 degrees. Right? And the reason the title of this slide refers to it as self-similar growth is because when the curvature of the streamline vanishes, there is no length scale that one could identify with this picture. But when the curvature exists, there's a curvature given by the length scale, and you can't rescale the picture by making it bigger or smaller and retaining the same shape. The only case in which you can retain the same shape is given by the central figure C. So to give you an idea how we can make these conclusions, I'll show you some features of the theory in the next slide. The calculation is done in the complex plane. The physical plane is there on the right. That right-hand side is what I've just shown you. And the blue feature, the fishtail bifurcation, is mapped by a conformal map to the real axis in the mathematical or image plane given on the left. And in the image plane on the left, or the complex plane, one can straightforwardly solve the Laplace equation. The open circles are the bifurcated tips. The green circles are correspond to the edge of the parent stream. You can solve the problem in that plane mathematically. And excuse me one second. Solve the problem in that plane mathematically, and then you can remap it back to the physical plane on the right. Right? And the reason one does that is because you can get an equation for that red streamline. And when you get the equation for the red streamline, you can calculate the curvature that goes into the tip. And from that calculated curvature, we can end up with the formula that you see below, in which the curvature for a given angle alpha scales like that quantity you see times 1 over v, where v is the vertical coordinate in in the image plane, you can think of it as a kind of arc length variable, right? And then the remaining terms are of order V. And so the point is that that first term vanishes. The leading order term vanishes when the angle, when the quantity in the parentheses vanishes, and that's when that angle is 2 pi over 5 or 72 degrees. Otherwise, in fact, it turns out to be infinite because of it's multiplying 1 over v. So it's either zero curvature or infinite curvature. And the point is, it's the vanishing of the curvature is where the problem becomes self-similar. And our, if you agree with our assumption that the growth will continue in the direction of the streamline, that growth will then describe a bifurcation, which is 72 degrees. So we now go to our network. The features on the lower left are the ones I showed you earlier. There's actually much more, and this is a picture showing you some of the features around that field site with an even bigger network. And it turns out that there's even more, and that'll be in this slide. I'm having trouble here. Let's go here. Have to wait for it to move. There. That's the whole network we have access to. There's nearly 5,000 junctions there, and we measure the opening angle of all 5,000 junctions. And the opening angle of these 5,000 junctions, we then make a histogram. And from this histogram, which is given here, you can see that the angle very nicely as a mean of 72 degrees. In fact, it's 71.9 degrees plus or minus about 3/4 of a degree, and a very large variance. This is what you get from all 5,000 angles. There doesn't seem to be much dependence of the mean or the variance on scale if we examine only first-order junctions or we look at junctions of other sizes, of other orders. So we take this to be a very positive result. The theory predicts 72 degrees. Measurement basically gives 72 plus or minus 1 degree. The variance is an interesting question. Our best understanding of it at the moment is that it comes from interactions within the network. The theory, of course, is simply for a single bifurcated tip in an infinite field. The network is growing, in some complicated setting, and feeling all the other boundary conditions around it. And there are obviously other sources of variance too, just the natural inhomogeneities of the subsurface, various kinds of random forcing, and so on. Okay, so I'd like to, in the remaining time, I'd like to talk about some ramifications, so to speak, of this work. One is that what we've shown here is that the geometric feature that we've studied, the opening angle, it arises only from external forcing. So it's important to realize that in our formulation, when the water leaves the subsurface, it also effectively leaves the theory. So it's all about subsurface flow. We've said nothing about how the water flows in the streams, and we've said nothing about how the sand flow in the streams. So this is not a problem in which the flow of water and sediment in streams is influencing the planform geometry insofar as we've characterized it, that is, in terms of the angle. Right. And so this one thing you can say then is it's counter to hypotheses suggesting that the bifurcation angles result from the minimization of energy dissipation within the streams. And this is this type of idea has had some success in biophysics, but it doesn't seem it doesn't seem necessary, at least for the problem we've studied. A corollary to that idea is that there's that energy dissipation or minimization of energy dissipation has some influence on the structure of the network itself, and we would say that our work suggests that that's not necessary. It's basically a consequence of the physics of the flow. Okay. Next, I have a few minutes. I'll just take you quickly through some things you can do with this. We of course have an interest in a more general model of how such networks grow. What follows is just a first attempt at characterizing it, and without belaboring the point here, I just want to say that at each stream tip, one can solve for the groundwater field and basically consider it to be an expansion in the square root of z, right? And which z would be the variable in the complex plane. And those first three coefficients are interesting. The first one can be related to the velocity of the flow. The second one to curvature of the streamline, and the third one, as I'll show you in a moment, to splitting of the water table. Right. And those three observations lead to some interesting statements. First equation up there corresponds to what you get when the water table is symmetric in front of a channel head. And the diagrams below that basically give a cross-sectional view of the height of that water table as seen from an observer looking outward from a channel tip. And you'll see there's a particular coefficient that we call AC, and when or a particular quantity that we call AC, and when the coefficient A3 is smaller than a certain quantity, the water table develops two humps instead of one. And one hypothesis that we have for what makes channels split is that the water table effectively starts to appear split in front of the channel. So that gives rise to a bifurcation rule, essentially, that one can, which is written there below in blue, and then one can implement that rule in a numerical model. And that's what the next slide shows. That's interesting. That's what the next slide would have shown. Hopefully there's more after that. What is happening?
I'm sorry, Dan. That's actually the first time I've seen that one.
Can we get further? Okay. Yes, we can, but it obviously is unhappy with, let me go back one and see what happens. No? Okay, so we're missing one slide. You know, I'm going to give some references at the end of the talk. You can find it. One of the references. There was in that slide a picture of numerically simulated networks, similar to the one you see here on the left. So, in a sense, you're seeing enough now. This is the type of network that you can generate, and one of the things that I was going to point out is that we discover from such simulations that there are these shapes which can be characterized as a logarithmic spiral. And the way that comes about is that you come to a branch point, you split, and then you split again, and you split again, and you split again. And because you're always branching at 72 degrees, in this case, or whatever angle you wish to branch at, it basically follows this spiral shape. And the diagram on the right is a characterization of that. And in passing, I'll point out that that yellow triangle is known as the golden triangle because it, in that golden triangle, has some relation to the golden mean, and it, in this particular case, it's related. And the golden mean has a relation to the 72-degree angle. So just to point out that this is not a imaginary feature. You can go to the Florida network and you can see similar structures. So that's what you see here on the left. And on the right is simply a confirmation that the branch points are coming about at distances which are decaying exponentially, which is what you would expect with a logarithmic spiral. That brings us to the conclusion. Basically, what we've done is describe the growth of a network as a growth in a harmonic field. That means growth in a field characterized by Laplace's equation. And what you can see is that this has allowed us to nicely characterize the angle at which these types of networks ramify. We've made a point that the control on the geometry is effectively extrinsic. And by extrinsic, we mean that the geometry is controlled by the field external to the network, not by the flow within it. And lastly, as I'm sure some of you have noted, what we've done is to predict the bifurcation angle, but we really haven't said anything about how the bifurcation occurs. We've just told you at what angle it needs to happen at. So that's obviously a point for future work. And finally, some references. And the missing figure for the numerical simulation you can get out of the first reference above, which was published about 5 days ago. So good timing. Okay, thank you very much.
Well, thank you, John. Daniel. I was hoping to be able to present myself some presentations with complex variables, but I've always been afraid to do that because of the the audience here. I appreciate your taking the effort to do that here. I had a quick question here. Well, before I ask my questions, I'd like to open it up to the audience. If you would like to type in a question, or if you'd like to unmute your phone and ask a question that way, feel free at this point. Let me ask my question. You mentioned precipitation. Is that net precipitation, less evapotranspiration, or did you actually use the raw precipitation?
To fit the data, it was just the raw precipitation. There may, of course, be a difference, but at the scale of that log-log plot, you won't. There were several orders of magnitude in that log-log plot, and it would have shifted the noisy data up or down by a little bit. So that's a good point, though.
But I think in that part of Florida where you have such heavy precipitation, the effect of evapotranspiration may not be significant. Well, go ahead.
It's a wet environment, right? So, yeah.
But this is a testable hypothesis, right? I mean, I'm just wondering, could you actually manipulate this experimentally to see by either removing groundwater or recharging groundwater to actually cause something to move about?
So what we really need to do is to monitor the water table. And one way of doing that is to monitor the flux coming out of it, right? And so we need to do that and monitor the rainfall rate at the same time. And that hasn't happened yet. We have one data set which is simply too crude. It's too crude in time, and it's and the associated rainfall data is too far away. It's at Tallahassee Airport. And so we're working on that. And obviously, it'd be nice to drill a hole too, but that's harder. It's about 20 meters deep, the water table. Could be done.
I'm just imagining if you were to pump a well in the vicinity, would that affect the direction of the flow field and thus the bifurcation angle?
Oh, but the bifurcations occur in geologic time. So, it's not only not on a graduate student's thesis time scale, it's not on ours either. It's slow. Like I said, a good guess for the growth rate is 1 millimeter a year. Of course, there are tiny bifurcations that grow within the valleys, but it's a long time to wait until you really have to, get to a scale of on the order of 100 meters before you know if this thing is going to grow or not. So it's a long wait.
You showed the picture from China. Have you compared your bifurcation angles with other geologic areas? Would you imagine?
Yeah, that's ongoing work. Hans-Jörg Siebold, one of the authors of this work, will have an AGU talk about that in next month. And he's analyzed bifurcation angles for all for the entire continental United States. It's available in one of the standard databases. The results are really interesting, and they basically show that the results that I've described in this talk are appropriate for wet climates. Right, that's where precipitation is exceeding evapotranspiration, but not appropriate in dry climates. So there's an interesting transition. So I don't want to take all of Hans's thunder, so to speak. So I'll refer to that, to the talk he's going to give next month.
Good. And audience questions? Can we get somebody from the audience to contribute? Well, thank you, Daniel. I'm sure people can approach you offline here.
Okay, thanks a lot.
Thank you.
Thank you, Dan, and I'd also like to thank Todd for hosting this series this fall. And once again, I'd like to remind everyone that starting in February, we'll have another series. This one will be focused on snow hydrology. So thank you very much, everyone, for attending.
Thanks a lot.